Hello all, and welcome to set 6, week 2. You will probably notice that this video got posted first. That's because the first video I did set 5, my computer crashed and I lost the recording. Very happy about it, but I will have to redo that video right after this one is posted, hopefully. So let's start with set 6. Set 6, we're going into chapter 3 in 2D motion. I've already begun the work here, starting with problem 3 in chapter 3. All right, so question 3 says a miniature quadcopter is located at x equals 2.00 meters and y equals 4.50 meters at t equals 0 and moves with an average velocity having components v equals 1.50 meters per second in the x direction and v equals negative 1.00 meters per second in the y direction. What are the x and y coordinates at t equals 2? So see, I've written what we know here. We know that t equals 2. We don't have xf, which is our final x location, which is what we're looking for. We do have our initial x location. We're given that at 2 meters. We have our average velocity in the x direction, which is 1.5, and we have that acceleration as 0. So if we pull up our kinematic equations that I will post online for you, we see that this is the simplest equation that we can use to solve for this. We know that delta x is just delta f minus delta, delta x is just x final x minus x initial, and plugging everything in to that equation above, we get x equals 5.00 meters. Final y coordinate, again, we are given the same information. Plugging in what we have, we're going to find that our final y coordinate is 2.50 meters. And our problems are solved. That one was very simple, a good way to start this chapter. All right, now number 4 gives us a little figure here of an ant moving in both the x and y direction. So let me just mark here where the ant is, 0.150 and 0.350. All right, so first question is, what is the displacement, which is delta x? We are given time is 5 seconds. We are given on the graph v initial in the y direction. We are given v initial in the x direction. We are given both x and y coordinates of both the initial and the final. And we have, again, in the x direction and the y direction, the velocity. So we can see here on the little graph, the red is our velocity direction. This is completely in the x direction. This one is completely in the y direction. So if this velocity had both x and y coordinates, we would see something like that, or something that looks like this, or like this, and we don't. All y, all x. All right. So let's get to solving some problems. We're looking for displacement. Delta x is just final minus initial. We are given that in the figure. Just plug in our values, we get 0.300 meters. We're going to do same thing for y. We are going to subtract final y minus initial y, and we get 0.200 meters. All right, so moving into B. B asks for what the average velocity is in both the x and y coordinates. So we know that average velocity is just delta x over delta t. We have delta x given in the problem before. T is given in the question. Plug in our answers, plug in what we're given, and we get 0.060 meters per second average velocity in the x direction. We're going to do the same thing for y. You see here we get 0.40 meters per second in the y direction. All right, so this takes us up to where I got. So average acceleration between the two times. Average acceleration is just going to be difference in v over difference in t. Again, x. We got 5 seconds. And our initial v is, what is that, 0.100 meters per second. And we get 0.020 meters per second squared. Okay, we're going to do the same thing for y. And we get final y minus initial y all over TF, because we're starting at 0. And we have 0.100 over 5. And we get 0.020 meters per second squared. All right, another relatively simple problem. All of what we're given is here in our graph. We just have to know how to read our graph. Okay, so now we want to move to question 5. Question 5. A car is traveling east at 25.0 meters per second when it turns due north and accelerates to 35.0 meters per second, all during a time of 6.00 seconds. Calculate the magnitude of the car's average acceleration. Okay, so let's start by drawing what's happening here. So this is directional. So let's do this. And if we have what we did with the ant, or what we were given with the ant, we have y and x. We are traveling at 25.0 meters per second. When suddenly we are accelerating north at 35.0 meters per second. So path is gonna change. And our time is t equals 600 seconds. So let's do what our book has done. This is 25. And this is 35. So again, we can see that both of these accelerations are completely in the x or y direction. So our final velocity is completely in the y direction. Our initial velocity is completely in the x direction. So we have VI equals 25.0. And that is in the x direction. We have V final in the y direction. And it is asking for average acceleration. Well, we saw in our last problem that average acceleration is just the change in V over the change in T. So let's do that here. We have VF minus VI all over T. And we get Now our final velocity we see has no x direction, so we're going to have 0 minus 25. And what we get is something that looks like this. Using our proper significant digits, we have negative 4.17 meters per second squared. All right, now let's do the same in y. And we've got Fy minus Fy over t. Now our final velocity is 35.0 meters per second minus 0, 6.00 seconds. And plugging everything in and using our calculator, we get 5.83 meters per second squared. Now, it is not asking for the x and y components. It is asking for the magnitude of the car's acceleration, or it's the hypotenuse of its triangle made by the x and y components of v. So let's draw a triangle, and using that triangle, we can figure out what our magnitude is. So here's triangle. And if you recall, we had this. We had that was given to us. Professor gave it to us in our first discussion printout. This just says that the hypotenuse squared of a right triangle equals one side squared plus the other side squared. We want this. So it's going to be square root of the, we want acceleration, not velocity. It is going to be squared plus and plugging values into your calculator, you get 7.17 meters per second squared. All right, now finishing with number 6. All right, so again, let's start by drawing a diagram, like the ant diagram. A rabbit is moving in the positive x direction at 2.00 meters per second. So a little bunny hopping. He's moving at 2.00 meters per second. And he spots a predator and he accelerates to a velocity of 12.0 meters per second along the negative y-axis, all in 1.50 seconds. Determine the x and y components of the rabbit's acceleration. Okay. So I'm just going to do this. Oh, sorry, I wrote this wrong. I'm going to do this. No, I was right the first time. 12.0 meters per second. All right, again, we have all x or all y components for our velocity. So what are the x, y components of the acceleration. Again, average acceleration is just going to be change in v over change in t, like we did before. In the x direction, this is all in the x direction. So our initial velocity is 2.00 meters per second. Our final is 0 over our change in time. We are given that in our problem, 1.50 seconds. And if we use our calculator, or you may be able to do these simple ones in your head, we get 1.33333 meters per second squared. Using our appropriate significant digits, we get 1.33 meters per second squared. All right, AY. So for this, our final velocity is 12 meters per second, and our initial is 0, all happening in 1.50 seconds. 12 divided by 1.5 is 8, using significant digits, 0 meters per second squared. Is that it? Just the A and B? Oh, I guess so. A and B. All right, so that concludes our video for set 6. I will see you soon redoing set 5 and moving on to set 7.